research project in Materials Engineering department. The topic of my presentation is prediction of mechanical properties of 3D printed metals using some machine learning techniques. So from the title itself we can get that there are three different subtopics involved in this research work. So one we have is 3D printing. Secondly, we have some metal systems we are investigating, and thirdly we have machine learning techniques which we are using to do the prediction. In this case we are predicting the mechanical properties. So first let's start with what is 3D printing. So another name for it in technical terminology is additive manufacturing. So additive manufacturing is basically deposition of, in this case, a metal which is done point by point, and over time we are able to build layers of metals and finally get a component of a desired shape. So in metal additive manufacturing community there are mainly two techniques which are very popular and widely used. So first of these is laser melt deposition, which is also called LMD, and the second one is laser powder bed fusion, LPBF. I'll briefly explain what are these techniques and how they work. So both of these are laser based techniques and both of them use metal powders to do the printing. In case of laser melt deposition, we have a nozzle and there is a laser coming from in between the nozzle from the metal, and then we have metal powders being fed from the sides. So when the laser is focused at a particular point, we get very high temperatures. It can be up to around 3000 or 4000 degrees Celsius. So at that point the metal powders which are being fed, they melt, and as the laser moves away they will solidify, and as a result we keep getting deposition of metal as the laser moves away. So this scanning happens line by line, and over time we will be building layers and we will get the desired component. The second technique, laser powder bed fusion, it also uses laser, but here we have a bed of powder. So in this case the laser scans over the bed of powder in a similar way, and the metal melts and then solidifies. But once a layer has been made, then the next layer of powder is added, and again the laser will go over that. So in this way, layer by layer again the deposition happens and we will get the final component. So now that we have understood how these techniques work, I will go to the next subtopic which is involved in this research work. That is, which metal alloy system we are using. So we know that normally the metals which are used for daily appliances or for other applications like aerospace or automobile applications, they usually have a single element which comprises of most of that alloy. So we might be having a single element alloy or maybe a binary element alloy, and there might be other elements, for example in case of steel, which are in trace amounts. But there is one alloy system which has gained a lot of novelty and is very attractive nowadays, and it is called high entropy alloy system. Another terminology which is used to describe it is multi-principal element alloy system. So in this alloy system, instead of having one or two elements which comprise most of the alloy, we have multiple elements which can be 4 to 5 elements. So one very popular multi-principal element alloy system is cobalt, chrome, nickel, manganese, iron system, which is also called Cantor's system. So in this particular system we have these 5 elements which are in almost equiatomic ratio, so almost 20% of each. And the amazing thing about this alloy system is that all these elements, even though they are different, they mix up randomly and they form a single phase. So we won't have many different precipitations or different kinds of entities in our metal which can lead to degradation of properties. So this is a schematic to show how atoms are arranged in a multi-principal element alloy system. And as you can see, there are different colored atoms which signify different elements, and they are all randomly spread. So why is this particular system attractive? It is because it can show some really attractive properties when compared to other material systems. So this is an anti plot, and it tells you how material systems perform when we are looking at multiple properties. So here we have fracture toughness on y-axis and heat strength on the x-axis. And we can see that high entropy alloy is on the rightmost, top rightmost. So it has high strength as well as high toughness. Why is toughness important? So toughness is important because even though we want to be able to apply high loads to our metal, we also don't want it to fracture catastrophically. We want it to fail slowly, because in that case we have a safer material. So that is why the high entropy alloys are so attractive, and we treat as why they show such good properties. One reason is that we have different atoms. So these are of different shapes. I should not say shapes. These are of different sizes. So even though they are all mixing together, there is some distortion in the lattice because of the different sizes and modulus. As a result, atoms find it difficult to slip past each other. So because of this, we are able to apply higher loads and they are able to withstand higher loads. Another reason is twinning phenomena, which happens in case of these alloys. So in these alloys, what we observe is, if we look at this particular micrograph, this shows you an image of what the metal looks like at a very high magnification. So we have different grain boundaries. These are different grains of the metal, but along with these, we have these stripes. So these stripes are called twins. So what happens is that these boundaries normally obstruct the motion of slipping of atoms, but these stripes also can contribute to the obstruction, and as a result we get even higher strength as well as high ductility, which is also important. So now that we have understood the alloy system, I will come to the methodology involved in my work. Before this also I will touch upon what is machine learning. So in very simple terms, machine learning is a computational based technique which can be used to identify patterns in data sets by using some mathematical algorithms. So in this project, we first started with collection of data. For this we went to literature, which was on the topics which I just discussed, and from that we collected data points and the parameters of different parameters which can describe the process of 3D printing. So these parameters could be the laser power or the scan speed used during the printing. It could be the composition related parameters, like how much of each element is there, or it could be testing related parameters, like what was the strain rate at which you are testing, or what is the temperature at which you are testing. So once we had our data set, we wanted to see how the data set is, how much variability is there. So we did a feature distribution visualization. So after this we wanted to use the data set and do some training of models. So what we did was we split our data set into two different smaller sets. One was for the training set and one was the testing set. We fed the training set to the model and let it run. So the model tried to identify some patterns in this training set, and once it had done that, we wanted to see how the model will perform if it is given some new data which it has not seen. So we fed it with the testing set, and from that we could get an idea of how the model is performing, how accurate it is its prediction. Once we had got a well predicting model, we wanted to also see how robust is it. So it was able to test this new data set, but if we are having some other kind of data, and if we are feeding some other data to it, will the model still be able to perform as well? So for that we did a split analysis, data split analysis. Once we were sure that we have a robust model and it is predicting accurately, we wanted to get some physical insights from the model itself, so that we could get an understanding of how the model is able to do the prediction. So to do that, we did a SAP analysis, and from this we could get a variable contribution effect. We could get the understanding of how the variables are contributing to the particular prediction. So once we had collected the data, we made different feature visualization plots. We did it separately for the LPPF technique and for the LMD technique. So we did it separately just because these techniques are different, and the parameters and the magnitude of the parameters involved are also different. So from these two plots, we can see that most of the data lies in these boxes, but there are some points, some data points which are feature values which are outside this range. And also we can see that there are certain data points which have outlier feature values. So these are quite different from the mean values, which can be given by these, which can be seen as these horizontal lines. So from this we can get a sense of what range of data we can, in what range of data we can expect the model to be able to predict well. If we give it a data point which has features which are outside this range, we can expect that the model won't predict so well. So once we had tried to train our model, we compared it for different algorithms. So we didn't just go for one particular machine learning algorithm. We chose three different algorithms. One is random forest, the other is gradient boosting, and the third is extreme gradient boosting. So we did the modeling, and once we were getting good accuracies, we made a comparison of how each model was performing. So to understand how a model is performing, we have certain metrics. One is called PCC and another one is RMSE. So PCC basically gives you a correlation between the actual experimental value of the property which we are trying to predict and what is the prediction that ML is giving. If the correlation is high, we can say that the model is predicting well. The RMSE gives you a sense of how much error is there in your prediction. It stands for root mean square error, and if the error is high, we can know that the model is not predicting so well. So we ideally want PCC to be high and RMSE to have a low value. In this case, we are interested in what is the accuracy for the test set, because the model had not seen it when it was trained. So here we can see that the test PCC are both, or for all three, they are above 0.8, which is a pretty much acceptable value. So we can say that we have been able to train our model well. Now we wanted to see how robust it is. That is, if a different data set is fed to it, will it still be able to perform as well? So what we did was, instead of using the original split of training and testing data, we made three other splits and we used the same model architecture. We didn't change that architecture. And after feeding these new training and testing sets, we saw how the model was performing. When we made this comparison, we could see that there are slight changes in the accuracy, but still it's not so much, and we can say that the model is pretty much robust. So now that we have a well-performing model and we know that we are able to predict the final property, which is the yield strength in this case well, we want to see what are some physical insights we can gather from this particular well-performing model. So we did a SHAP analysis, which is also called a feature importance analysis. In this we look at how the model is, how much weightage the model is giving to different features when it is doing the prediction. So using this analysis, we can get a hierarchy of the variable contributions. So in these two plots, you can see that there are different parameters related to the printing process, and the first one is scan velocity. So the order of these parameters tells you how much importance the model gave to each parameter. Scan velocity had the highest importance. Also, another information we can get from these plots is these colors. So here you can see there are light blue colors and darker colors. The light blue colors mean that the particular data point had a very low value. The feature had low value for a particular data point. The darker colors mean that the feature had a much higher value for that particular data point. So here we can see that the lighter colors are on the left side, on the negative x-axis, while the darker ones are on the positive x-axis. So what this tells us is that if the value of this particular feature, scan velocity, which is the velocity at which the laser is moving, if this particular feature is high, then we can expect that the property value, which is our yield strength, will also be high. Similarly, for laser power, we can see that it's the inverse. If laser power is high, we get a lower property value. So, what could be the reason for this? Why is the model attributing higher property value to higher scan velocity, but a lower property value to the lower laser power? The reason we can understand, we look at the physical process, is that when you are doing the scanning, if the scanning is very fast, the amount of heat that is going at a particular area, it will be lower. As a result, we can expect that the solidification will happen very fast because there is no amount of heat. And if the solidification is fast, we can expect smaller grains. So, as I was saying, we can expect smaller grains if the solidification is fast. As a result, we have lots of grain boundaries. So, as I showed in the previous schematic, if we have lots of grain boundaries, they will act as obstructions to the slip of the atoms. So, we can expect that if we have a slower scan velocity, the smaller grains will lead to a higher strength. Similar kind of explanation will also go for laser power. Higher laser power will mean that we are inputting more heat into the material, and as a result, we have slower solidification, larger grain, and a lower strength value. Similarly, scan pattern also showed a quite significant effect. Scan pattern is basically how the laser is scanning. So it can scan in different ways when we look at different layers. So the layer orientations can be different among the layers. That will also have an effect on what is the final strength. Similarly, the composition also has an effect because of different sizes that different atoms will have. So the key result of this work was that we were able to successfully show that the mechanical properties, in this case yield strength, can be successfully predicted for additive manufacturing of metals. So this was all good, but what are the implications of this particular research? How can we take this research work forward? So the novelty of this particular work, I feel, is that it opens many doors for the additive manufacturing community. This is a first of a kind work which tries to do bulk property prediction for additive manufacturing. And the reason this has not been done before is that if you look at other modeling techniques which are more physics based, then it is very difficult to do the simulations or the modeling because it's very complicated. Lots of phenomena are occurring at the same time when you are doing 3D printing. So in that sense, this has opened up many doors for the community. And how can we take this research forward? So it can be possible that we can conduct physical experiments to further validate the models we have. Also, we can look for more data points so that we can predict other properties like the ultimate tensile strength or the elongation, like uniform elongation that the material shows. But the ultimate vision we have with this particular approach is to be able to identify certain parameters. It could be compositional or printing parameters or testing parameters, which will be able to give us tailored properties. So, if we are able to do that, firstly we will be able to get materials of the property we desire, and secondly we will also
just back of the
be able
case,
to
no
wipe
one
out
to, because the scoring will not be novelty.
which are involved when you want to make a dense print. Because of various
Here
which
also.
can easily come up when you are doing 3D printing, the parameters are important.
Yeah,
If you have these kinds of prediction techniques, you can bypass a lot of the experimental iterations that are required, and in this way you can save a lot of resources as well as a lot of time. So this is a small work, but it is a work in the right direction and there is a long way to go with it. Thank you. So I would like to end with the Q&A session.
So any questions for your participants? So talking of it's a very interesting work, and it just shows us the versatility of AI techniques, how they can be extended to very radical applications. So I have just a very layman question to start with. What is the implication of data sets? We know there's some thumb rules that we need to keep in data sets. So what do you generally keep? What are these thumb rules while applying data sets on machine learning algorithms?
When you mean preparing data sets which can be used later on to feed into the algorithm.
Like for example, in this current problem, you said you got your data sets from literature. So did they meet all the thumb rules generally that you have for these data sets?
Normally, we don't really have any hard and fast rules when it comes to data. What we endeavor for is to be able to describe the process well by using those particular features. If there is anything missing, the model might not be able to predict so well. So that is what is our primary concern. And also there are some techniques which we can use to clean up the data to make it more accessible for the model, like normalization or removing outliers, those kinds of techniques. But other than that, I think there is nothing.
Current problem statement. You had multiple design parameters like the percentage of the 5 elements and the scanning. So when you are taking the data, did you get a good spread of these data so that your model is general enough? Will you keep that? Was it ensured?
So we tried to ensure that we had a good spread of data because that is also important when you want the generalized model. So we did that feature with distribution visualization to get a sense of how much variability we are getting for different features. I think that will partly answer your question. And I think we had got a good distribution of feature values. So I think we were good in that space.
On the training data sets, you got it from literature. For this, what are the alloy you tried? It usually requires large data sets to train the. That much data you are getting from open literature.
So normally this is a common problem we have when you are doing materials informatics related studies, especially if it is experimental. So we try to get as much as is possible for single phase MPA systems. We got around 130, 128 to 130 data points, and we did a 80 to 20 training students. I think it was pretty fine to make sure that the data set was not too sparse. We did the this split analysis, data split analysis. So after that we felt that we were able to predict it quite robustly.
And then the standard deviation, the last graph you shown with this standard deviation 100 megapascal.
Yeah.
One it looks higher.
Yeah.
Why that much uncertainty?
Yes. Yeah. So 100 megapascal, I just go back to that slide. So the range of E strength we had for our data set, it was from around 200 to 800. But the variability we are getting is almost 100.
Yeah.
So one very major reason for this is that the different printing techniques, even though we are looking at a particular printing technique, the machines that they are using might be different. So there are some parameters which are quite specific to the printing array. So for example, what is the spacing between the layers, or what is the diameter of the laser you are using. So those also can have some effect. So they will average out, but some variability will come because of it. So I think that is the major source of the variability we are getting. But we are able to show that it is possible to do some kind of prediction and get some insights from how the from how the model is predicted.
That was a very good presentation. So I just want to ask one question. So you were relating the scan velocity and power to the metal properties, right? But you were concluding that the higher scan velocity got better properties, and when you are giving more power, you got actually not so good properties. And you are more like explained with respect to the heat that has been going into that point. But if you see, if you are like having a high power and a high velocity, then the heat that is going there will be minimum. So that way, these two parameters are actually connected, right? So ideally, power intensity will be like a parameter you should have been chosen. So
Power and density, yeah, they are
power intensity, I'm saying.
Okay,
Like
power.
like you're having
Yeah,
laser
yeah.
power and deep velocity. So
Yes,
and
I
you are
agree.
more concerned about the heat that is going there. So
Yes.
if you are connecting these two parameters and making it to a single parameter like power intensity or power per velocity or something like that,
Yes,
so that these two parameters are not separate.
yes.
So that will be a better way, right? So what do you think of that?
Yes, sir, I think that will be better way. So in this case, let me go to my contribution slide. So we have two other parameters. These are energy densities for the LMD and LTBF technique. So we also incorporated this. But the reason we still kept scan velocity and laser power is that there is not a direct relationship between these two and the energy density. There are some other variables which also come into the picture, like what is the spacing between the scans you are doing, or what is the diameter of the laser, because that affects how much is the density of energy, what the energy density, power that is going in. So we were not sure about how exactly these might be connected. So we wanted to ensure that we are giving it as much information as possible. So we kept the scan velocity and laser power also.
So, any questions from the audience?
So I just maybe one last concluding question. So like, have you heard of this concept of in situ manufacturing, or in the context of additive manufacturing? Like you must have heard about these very large rocket engines now being made, nozzles being made entirely out of additive manufacturing. So what do you think will be the challenge of these? Like when you go make settlements on Moon or Mars, like come to in situ, what would be the challenges that you face in that context?
So you, by in situ, I think you mean that you are doing the manufacturing and then you are not doing any post processing. You are directly getting the form.
So the manufacturing plus the raw materials will be extracted from the environment itself.
Okay.
So in
So
that,
if we specifically look at metal additive manufacturing, one major issue or one major obstacle is that we need metal powders which are spherically shaped, and the purity and the surface morphology is also important. So that is a constraint that we have. So if we are in a new environment, it might be difficult to obtain those. But other than that, I think if you have the right parameters, then you can print any component with quite reasonable amount of densification. So the only constraint we have is the powder that we have to feed in, as well as the sophistication of the sophisticated equipments which can require some high amount of power, as well as some conditions which might not be available at different places.
thank you very much.
Thank you, Chandrakant. Thank you, Asina. So, next I call upon